Right then, this video is going to go through exercise 12, 13 and 14 through the practice paper. And these are the last few questions. So we're going to look at dipoles and intermolecular forces here. So exercise 12 is a tricky one to do, especially without the electronegativity data. So I'm just going to quickly put that here. Fluorine has electronegativity value of 4.0. Hydrogen, let's check what it is on your paper. Go with 2.1, but this varies. Sometimes it has 2.2, 2.0. For this example, I'm going to say it's 2.1. Oxygen, 3.5. And bromine, 2.8. So we've got there our four values. And the first one it wants us to do is fluorine bonded to fluorine. So I'll put the values then just below. We've got exactly 4 and exactly 4. So what the electronegativity data tells us is how well it's going to pull these two electrons towards the atom. So you've got fluorine pulling with a strength of 4, this fluorine pulling with a strength of 4, so they stay right in the middle. So in this is a non-polar bond is formed. We don't get a dipole. So I won't draw on delta plus, delta minus on either side. And that's the same no matter which two elements are bonded together. If it's bonded to itself, it's always going to pull with the same strength. Next up, we've got oxygen bonded to hydrogen. Now, this is water. So I'm going to change pens in a sec. So in this one, we've got oxygen at 3.5. Our hydrogen's at 2.1. So there is an electronegativity difference. In this bond, the oxygen's going to pull more, and also in this bond, the oxygen's going to pull more. And that's going to make our oxygen delta negative, or slightly negative, because there's more electrons around it now. If it's pulling these electrons towards it, then they become slightly negative. Now the hydrogens are going to become electron deficient. So each of them becomes delta positive. Now we've assigned our dipole to that water molecule. Our final one is HBr. And HBr has hydrogen at 2.1, bromine at 2.8. So this is above 0.5 electronegativity difference. So it's just strong enough to form a dipole, where the hydrogen becomes delta plus, bromine becomes delta minus. Because bromine is the stronger electronegativity, the electron's going to be pulled towards the bromine. Don't need to draw the electrons on. I've just done it to demonstrate that these bits are the important bits, the dipoles. So exercise 13. Next. And it asks us first of all, what is meant by an intermolecular force? And an intermolecular force is just the weak bonds that occur between molecules. So if we had a nice beaker, I'm going to have to draw too well with this pen, I'm going to try it with the brown, it's a bit better. So a beaker of a chemical and liquid solution. So let's say it's water. I'm not doing too well with drawing on this at the moment with these pens. There we go. So lots and lots, trillions and billions of little water molecules floating around. Now what keeps them all together in there are not the covalent bonds. It is the very, very weak bonds between the molecules, and there are intermolecular forces. So in this question, just sort of a pass answer, is that they are the forces that interact between molecules, or the forces that occur between molecules. So hexane molecules are held together in the liquid state by induced dipole forces. Explain how these arise. Induced dipole forces have lots of different names. I like to call them the London dispersion forces, sometimes called temporary dipole bonds, or even van der Waals forces. That's going out of fashion a bit. So the first thing that happens in an induced dipole is you get an uneven distribution of electrons in a molecule. So uneven distribution of electrons. And that looks a bit like this. I'm just drawing the electron cloud around a molecule. All the electrons go to one side, and that creates a delta minus and a delta plus. The next thing is that this induces a dipole in a neighbouring molecule. Hence where we get the name induced dipole from. So because this side's negative, it's going to repel electrons. It's going to push them all away. So we get two sort of squashed molecules where all the electrons have moved to this side, but that's forced in the neighbouring molecules all its electrons to move to that side. And then the final thing is they just attract to each other. We then get delta plus attracting to delta negative, and that is our induced dipole bond. So here, between the two, we get a little weak, very weak attraction. And that is how induced dipole-dipole forces arise. So, classic example in the next one is to compare chlorine and bromine. So a chlorine molecule is two chlorines bonded together. Bromine molecule is two bromine molecules bonded together. And which of chlorine and bromine would you expect to have the highest boiling point? Now, in order to get these to boil, you have to break the weak intermolecular forces between the molecules. So not the covalent bond, but these weak intermolecular forces. You've got to break them. In order to break them, we put energy in. And the stronger the bond, the more energy in the form of heat we've got to put in. So, first thing to mention is, we call them London dispersion forces. Strength is determined by the number of electrons. So whichever will have the most electrons will have the stronger induced dipole bonds. And we've got chlorine. Each chlorine atom has 17 electrons. But each bromine has 35 electrons, each bromine atom. So bromine's got the most electrons, so it will have the strong London dispersion forces. So in order to get this bond to break, we'll have to put more energy in than we would have to put that one in. So bromine will have the higher boiling point. The next similar type of question is comparing HCl to methane. Now HCl has a dipole. So we've got a delta negative chlorine and a delta positive hydrogen. And we've also got our methane that has no dipole. So in this, we're comparing permanent dipole bonds because the dipole is always there in this. And this one is just London dispersion forces, the weakest type of bond. And permanent dipoles are stronger, so this will require more energy to break. And we can see that in the boiling points. Minus 85 for this is a higher boiling point than minus 164. And it's just because of the different types of intermolecular forces they have. This one is stronger. Ammonia, very soluble in water. So in order for it to be soluble, it needs to be able to hydrogen bond with the water. So we'll draw our ammonia molecule, which I'm not going to stick to the shape perfectly. I'm drawing a rough kind of shape, not the 3D structure. And then we've got our water molecule. Now, definition for a hydrogen bond is an electrostatic attraction between an electron-deficient hydrogen. And we have that on both the water and the ammonia. So we could have a bond between this and the hydrogen, or this and the hydrogen. But this electrodeficient hydrogen is going to form with a bond with a lone pair of electrons on a highly electronegative atom, either nitrogen, oxygen, or fluorine. So we've got nitrogen with a lone pair, we've got oxygen with two lone pairs. So our bond, you can draw it coming from the nitrogen to that hydrogen, or even from this hydrogen to that oxygen. But the point is the hydrogen bond. Ammonia will hydrogen bond with water, and so they'll dissolve. It will be soluble in there. So in the question, I've got to include dipoles, got them in. These are the delta minuses, delta pluses, that's my dipoles. And I've also got the lone pairs of electrons. When you're drawing a hydrogen bond, you have to draw the hydrogen bond from the lone pair, not from the atom. So you see up here with the oxygen, I've drawn it from the lone pair, not from this oxygen atom. Next up, oh, I love this, we've got ethanol and propane. So got to draw in the dipoles on ethanol and propane. So we've got no dipoles in propane. Propane is just carbons and hydrogens, and they're not big enough difference in electronegativity to form a dipole. But in ethanol, we do have a dipole. We've got here an electron deficient hydrogen because the oxygen draws away, but it's also drawing away from the carbon as well. These are the important bits, and really should have two lone pairs there on the oxygen. So one is a gas and one is a liquid at room temperature. So it'll be the one that forms the stronger bonds into molecular forces that'll be a liquid, because it's getting held together as a liquid. Whereas if it's a gas, it's floating away and nothing's holding it together. So the ethanol will be a liquid because it can form hydrogen bonds. Got electron deficient hydrogen, got a highly electronegative atom in oxygen with a lone pair. So this can hydrogen bond, stronger bonds, be a liquid at room temperature. Propane will just be London dispersion forces, and ethanol as well will be the one that can dissolve in water, similar to why ammonia can. Get my water molecule out with a lone pair there. We'll have a delta positive hydrogen, delta negative oxygen, delta positive hydrogen, and we could get a lone pair here between that lone pair and that oxygen and that hydrogen, or from this lone pair to that hydrogen. So because they can hydrogen bond, it will then be soluble in water. And that is exercise 14 even. And that's the end of the mock paper. I hope you did okay on it. Any questions, send me some emails.